Hi, everyone. My name is Gabriela, Gabby for short. I'm a PhD candidate at Arizona State, working with Dr. Yoon Kang, and I'm very happy to be here. Thank you so much for inviting me. And Gail, happy birthday. We haven't really met, but it's been awesome being here and hearing from you and your academic family. That's been fantastic for me, so thank you so much. And today I'm going to tell you about one of hopefully the chapters of my dissertation, which is about thinking of social insects as model for different things, but in particular for how they do collectively, they collectively solve hard problems in a very efficient way, in particular with respect to defense in this case. So allocating resources to tasks efficiently is important for any organism and also any, like many artificial systems. So if you're an animal, you have to forage for food and you have to spend your energy in like reproduction and getting more food, and you have to decide how to allocate your time and your food and your energy. And even more if you are, for example, a colony of insects or just a group of individuals, you have to allocate your resources inside your society in a way that everyone gets what they need and all the demands are being supplied for. And there's basically two things that we're focusing on. One is resources are always finite, so you can't like over allocate resources to only one thing because that's a waste. And also availability of resources may suddenly change. So you may have a crisis in the supply of your resources, and you will have to respond to that fast enough, right? And social insects are great at these two things. So they are really good at just regulating how they forage when the food is changing over time, when the sources that they forage from are dynamic. And they do this with a high degree of diversity within colonies. So all individuals are different in the colony. They coordinate in an efficient manner without a central control, which is one of the most remarkable things they can do based on only like very simple interactions from one-to-one in one-to-one base. And also experimentally, they're really convenient to manage. They're really easy to observe, so you can easily get data from them when working with social insects. So that makes them really good models for just trying to understand dynamics for hard problems like allocation of resources. And then among the tasks that they have to solve, defense is one important one. And this is relevant for any group, any social group, including humans for sure, because social groups gather a lot of individuals and resources in one place, and that makes them vulnerable to opportunities from robbers or parasites to try to get in. And so they have to allocate some individuals to defense. And there's basically two ways in which evolution can shape that adaptation to collective defense. One is getting specialized individuals for defensive tasks, so like producing soldiers, and you'll see like some ants are like super big and they're like meant to defend a colony. And the other one is just getting everyone to be able to switch to the task that is needed very flexibly. So that would be not as efficient, but very flexible. So in case of a crisis, if you need extra individuals, then that would be very convenient. So we're gonna talk about a particular species of bees. It's called Tetragonisca angustula, and they are stingless bees. They are a really great model because they have a mixture of all these strategies at different time scales. So they have all the range of defensive strategies that you can think of in terms of efficiency and in terms of flexibility. So in the first place, they have morphological specialization, which means that they have two distinct sizes of bees. One is just majors, which are big bees, and the other one is minors, which are small bees. And the big ones are better at defense, right? The thing is, of course, the big ones require more food and resources to be invested into them. So this is called morphological specialization, but if you want to change the number of majors that you're producing, that will take a long time. It changes over evolutionary timescales because it depends on how they feed their larvae. So that's occurs in the time span of evolution, or at least weeks. And majors, so the big bees, will perform in-nest tasks when they're young and then switch to defensive tasks when they reach middle age. And this transition from one type of task to another, that's called age polytheism, and that's also common in other species of social insects. And it's a way of getting some flexibility in task allocation without doing full like specialization or just full flexibility. It's like you just change in the middle of your lifespan. And so this transition, this maturation to guard is taking the like days. It's like half the lifespan of a bee. And lastly, they have task generalism, which means that some bees are capable of changing their usual task to supply for demands. So miners, which are the small bees, they're not really good at defense. But if you remove the big guards from the nest, then the small bees will go out and replace those guards. So this is a crisis response from the smaller bees. So they're not specialized to do that task, but they can respond in a crisis situation. So we have 3 different mechanisms at 3 different timescales and in the span of flexibility versus efficiency. So we want to know in general, so what biologists ask are what ultimate mechanisms regulate these 2 things that they do so well, which is specialization, so the production of majors, and replacement, which is the most like flexible response. And ultimate in this case means not the proximate mechanism, which is just like you feed some larvae some more, and that's how you get your majors. But ultimate in the sense that how is this good for the colony? What is in an adaptive way? What is determining the number of majors you produce? So how many specialized individuals you produce? And then specifically, what we're going to study is how do the parameters regulating these 3 processes, so specialization, age-based polytheism, and behavioral plasticity or task generalism, affect colony size and task allocations, which are the 2 big things that determine colony survival and thriving. So I'm going to build a model. So first, imagine a population of size p. Right? It depends it changes over time. The eclosion, which is the version of birth in social insects, so they just emerge from their eggs as adults. It will depend on how many workers, so non-guarding workers, are dedicated to taking care of the brood. And this will be a saturating function whose maximum is the egg laying rate of the queen. So only the queen lays the eggs, and then all the other workers need to maintain those eggs and take care of them until they eclose. That's why it's a saturating function. If you don't have any workers taking care of the eggs, then you don't have any eclosure at all. This function has been used before in other social insect models. And then we assume that a fraction of the newly eclosed adults are majors, and then the rest are minors. So we have a fixed fraction of specialized individuals. And we also assume that there is perfect detection of guard loss. And what this means is that the minor guards, the ones that are not specialized, will, So the minor guards will, if the proportion of guards in the colony drops below the colony demand for guards, which I'm calling theta, then the minor guards will go and replace the major guards at a rate delta. And if the fraction of guards in the colony is above that threshold, then there will be no replacement. And this stands for non-crisis, this stands for crisis. So it's perfect detection in the sense of a step function instead of a graded response, which is more likely what's happening, but this is a simple first approach to replacement. So what's going to happen is the new adults will close. Some of them will be majors, some of them will be minors, and I'm using capital letters for the majors and lowercase for the minors. And then these are the 2 classes that are contributing to the eclosure of new adults. So only these 2 are actually taking care of brood. Then with time, the majors will be mature and become guards. So that will happen at a rate 1/tau. And it takes some days, and that's the age polytheism. And the minors, I'm sorry, and they of course will die after some time as guards. Then the minor non-guards will usually just live their lives as foragers and nest maintenance and then die, and that's it. But if there is a crisis situation where there's not enough guards, then they will go and replace the guards. So the proportion of guards that determines whether they replace or not is the sum of these guards and these guards. So if the sum of this over the total population drops over theta, then there will be replacement. Otherwise, it will not happen. And of course, as guards, they will also have their own death rate. So we have all the span of time scales in the model, and we have the slow feedback, so the regulation of major production, slow feedback for efficiency, and we have the faster feedback, so the crisis response as fast feedbacks to be flexible in terms of the colony. So with that pretty much illustrates what the equations are going to look like. So this is just a summary of all the parameters in case we need to go back. And the equations will look like this. So this first term is just eclosion. That's how the new adults come to be. And that will be some of them, just row of them will be majors, 1 minus row will be minors. Then the majors will be mature, they'll become guards. Both of them will die, and this is the regular situation where there's no crisis. But if there is a loss of guards, then there will also be replacement. And that will only happen if the proportion of guards drops below theta, right? And if so, it will happen at a rate delta, which is fast. Yes? Mu capital W. Why is there not a death rate for the non-guarding? Okay, yeah. That is a good question. I did not include it because I'm assuming that they are too young to die. They stay inside the nest, and that this is just an aging process, right? So they eclose, they work inside the nest, and when they're old enough, then they go out and die. So I'm just assuming that the probability that they will die at such a young age, before the maturation age, is not relevant enough to be included, and also not measured enough to get data about it. And that the lifespan will be determined by how long it takes for them to mature, and then how long it takes for them to die as adults. Yes. Yeah, because under usual circumstances, they will just not have this replacement, right? So under normal circumstances, they will just do this. So they will close, and then they will spend their whole life in between the nest and just foraging tasks, and then die. So this death rate will actually be, so 1 over this will be the whole lifespan of a minor bee. And that's what will usually happen unless there is a crisis situation, and only then will we have the rest of the terms. So this lifespan will be comparable to the maturation plus the death rate for these ones. That's all right. So that's the whole system, and that means there is basically 2 cases: when you have the replacement and when you don't have replacement. And they will be very similar systems of equations, just one of them has replacement and the other one does not. So for the majors, nothing really changes whether there's a lot of guards or not. But for the minors, you may or may not have replacement, and that's the 2 cases. The only difference is this delta W term that will appear in the crisis case, and that small difference makes 2 different vector fields that are determining the whole vector space, the whole variable space. So we'll have the function that determines which vector field is governing the system is whether the fraction of guards is high enough. And on one side, you will have just not replacement, and on the other side, you will have replacement. And this is a Filipov system, a very simple case of it. So you have 2 vector fields, F1 and Fs1 and Fs2, which are just with and without replacement, and then divided by this switching function, this boundary, which just says when the fraction of guards is exactly equal to the threshold theta, and then when it's below or above that. And then inside that, we have to classify equilibria a little differently. So we need to define, so when an equilibrium is inside its own vector field, but also has the right proportion of guards. So if the vector field for the crisis system has an equilibrium and that equilibrium has a low proportion of guards, then that is a regular equilibrium, it's okay. But then this vector field may also have equilibria that have a high proportion of guards and fall outside the correct region. And that would be called a virtual equilibrium. So it will not be reached because it's outside the region of the plane that's governed by its own vector field, but it's still an equilibrium of that vector field. So in that case, we just name it a virtual equilibrium. And then the other thing that may happen since we introduce this continuity manifold is on the switching surface, we need to understand what happens. And the things we care about are basically either trajectories will just cross the boundary when the vector fields kind of agree on the direction. And that if that happens, then we just say this point on the surface, on the switching surface, is a crossing point, and thus we define a crossing set. But in some cases, the vector fields will not agree on the direction. And in that case, we define its own vector field on the switching surface, which will only hold on those points that compose the sliding set. And this vector field will only be a linear combination of these other two vector fields. And it will have its own equilibria, and those equilibria are called pseudo-equilibria. And so they're just simply equilibria of this newly defined G vector field on the sliding portion of the switching surface. So we have that extra category of equilibria. So with all those tools, we can figure out what's happening in the system. So if you take separately the two vector fields, then you can find their own equilibria. Each of those internally have two interior equilibria and one extinction equilibrium. The extinction always will exist and is always locally asymptotically stable. The interior equilibria in each of the two cases, one of them is stable, one of them is unstable. So we have this strong Allee effect where if the population is really small, then it will converge to the extinction equilibria, and if it's large enough, then it will go to the interior equilibria. This makes sense because it's a social group, it's a bee colony, so it does need a minimum number of bees to take care of brood. And then at the switching surface, we have two pseudo-equilibria with its own existence condition, which is kind of a combination, also a linear combination of the other two existence conditions. And those will only make sense when there are sliding trajectories on the switching surface. So when the proportion of guards is exactly the threshold. So that's the general dynamics, but now we need to understand when we are in each of the cases, right? So when are equilibria regular? When are they virtual? Because if they're virtual, they will never be reached, so might as well not consider. So remember, what determines the switching is whether proportion of guards is large enough, and that's this operator here. And so it's useful to define the ratio of guards at each equilibrium. So if there is an equilibrium from the base system, base meaning there's no replacement, if this quantity is large, so if there's enough guards, then that's going to be a regular equilibrium. But if it's small, then it's actually a virtual equilibrium because it becomes the crisis vector field. So we can define those two proportions, gamma B and gamma C. We can graph them in terms of rho, which is the proportion of majors, and see how they behave. And that's important because we are interested in knowing how the proportion of majors affects the task allocation and colony size, right? So we need to understand to what equilibrium the system is converging for different proportions of majors. So about these two quantities, we can say some things that always hold. So, for example, the blue line, the number of the ratio of guards in the base system will always be less than the proportion of guards in the crisis system, and this makes sense because the crisis system has replacement, so it has extra help from the minor guards. So there's just an extra flow into the guards, right? And we can also say that the ratio of guards in the non-crisis system, so when there is no replacement, will be increasing with the proportion of majors. That also makes sense because if there's no replacement, then the only compartment that is contributing to the guards is the major W, so capital W. Then we can also say that the ratio of guards in the replacement system, the crisis system, may be increasing or decreasing according to this condition. And that condition is whether or not there is enough recruitments into the guarding compartment in the lifespan of a guard. So this would be, so 1 over mu g is the lifespan of a major guard, and 1 over tau is the rate at which majors are becoming guards. So if they are not entering the guarding compartment fast enough, then that will mean that the more majors I have, then the worse it is for the guarding proportion. So if if maturation is really slow, like here, then I will have a decreasing proportion of guards as I increase the proportion of majors because they're taking too long to become guards. And otherwise I have an increasing function. And this is the one that kind of makes sense since we're trying to capture 3 different timescales here, because this will only happen so that this mu g and mu lowercase g are fairly similar. They are death rates of guards, and once they're guarding, they're subject to more or less the same conditions. So it depends on whether the maturation is happening faster than replacement or not. And we are kind of saying that the maturation is should be much slower than the replacement, because replacement is a crisis response mechanism, right? It's fast. They should go out in minutes or hours, while maturation should take like days. So we are this is the case that we'll see when we plug in actual real parameters. But in other systems or other species or maybe artificial systems, you may have something like this, where you have a maturation process and a replacement process, and they're not necessarily that different in terms of timescale. So now you take those quantities, the gamma C and gamma B, and depending on how high the demand for guards is in the colony, then that will determine how the system transitions between the base and the crisis system as rho increases. So as I increase the production of majors. So for example, in this case, I have like both of the ratios are increasing with rho. But if I have a very low requirement for guards, if I don't need a lot of guards, then just producing this many majors is enough. And then from there on, I'm just at the base system where I don't require any sort of replacement. I'm fine. But if I'm in a situation like this, where the requirement for guards is a lot, so I need like half of the population to be guarding, then that means that if I don't produce enough majors, then I will need replacements for this, like at equilibrium, for all of these proportions of majors. Then in the middle, I'll have this sliding behavior, which is the pseudo-equilibrium, which also requires an endemic population of minor guards, which should not really be there. And then I'll only reach the base, like non-replacement equilibrium if I produce a lot of majors. What we actually see in real colonies is more something like this side. So if the demand for guards was unreasonably high, then I would just have replacements. I would need replacement no matter how much majors I produce. But if I just need a little bit of guards, then it will be more likely something like this, where I need to produce just a little bit of majors, and that will be enough. And that's actually what we see. Like actual colonies produce between like 5 and 6% of majors. So that's more of this case here. But one interesting thing to see here is if you were to think outside the stingless bees and just about any system that has this type of 3 distinct timescales of dealing with demand for specialized individuals, you would think, well, if I increase the production of specialized individuals, that should be good. That should help me get more allocation to guarding, right? Because these guys are the specialized ones. And that's not always true. Depending on the other, like on the demand and the replacement behavior, then as I increase the production of soldiers, I might actually get less allocation to guarding, which is kind of counterintuitive and worth taking into account. So this is just a summary of the whole system dynamics, and this is for actual parameters belonging to the stingless bees. So the actual colonies will live in this region. Of course, we don't expect real colonies to live in a crisis situation all the time. But what's happening is this is the proportion of majors. This is the replacement threshold, which could mean the colony demand for guards. And if you have, if you have a really high demand for guards, then quickly, so that this white region means just extinction. So if you ask too many guards, then your colony may actually not only need replacements, but become extinct, because replacements should be taking care of brood, and if they're not, then the colony may become extinct. So this replacement threshold actually bounds the region where the colony can exist, and also determines when it can exist, but with a constant input of replacement guards, which is not a biologically sustainable situation. So these are just simulations to illustrate how these this sliding and crisis and non-crisis dynamics look like in time. So the blue lines will be the base case, so no replacement is happening, and that's evident right here. So the minor guards are just 0, so they might be necessary at some point, but the colony is producing its own major guards, and that's enough to supply for the guard demand. So there's no minor guards. But you see, both in the pseudo-equilibria and the crisis dynamics, we have a persistent population of minor guards over time, and that's the equilibrium includes those, and we don't usually observe that in wild colonies. And the actual sliding can be seen here. So that's how the proportion of guards over time just is exactly equal to the threshold data. And this is just to further explore what the maturation time is doing, because we emphasized first what the production of majors is doing and what the replacement threshold is doing in terms of transitioning from crisis to non-crisis dynamics. But what's the actual maturation time doing? So if I have this maturation time, which is about 20 days, and that's actually what bees kind of take to mature into guards, then this is the colony size for different proportions of majors. And as I said, it's usually a small proportion, so it's somewhere like here. And the colony size would be decreasing if I were to increase the proportion of majors. And here you see this is the crisis equilibrium, and it's a virtual equilibrium, so it will not really be reached, but it only has its existence condition satisfied after this point. If I reduce the maturation time to 10 days, the bees usually live like 28 or 25 days, so it's like in the end of their lives. So if I reduce the maturation time to 10 days, then that might actually mean that for higher proportions of majors, I won't have the existence condition met for the base system. So the colony may not sustain a large number of majors at all. And if I keep decreasing, this is actually tau equals 5. If I keep decreasing the maturation time, then that existence condition will be sharper on the colony. So the colony will be able to sustain less and less majors if the maturation time is really short, which can also be important, because you might also think, if you were engineering the system, you might say, oh, I need this like to supply for this specialized soldiers, I will just like reduce the time it takes for them to become soldiers, and that will be good. But that actually may reduce the size of your group and also like sharpen the conditions on the existence of your group. So that's also, this is just the same graph that you saw before. So this was exactly the same, and this one is just reducing tau to 10 and tau to 5. And you see the region where the existence conditions are met keeps getting smaller here. So with that, this is just a deeper look into task allocation. So we saw the colony size for different taus. Now we're looking at the actual allocations of who's doing what inside the colony. And so this would be the biologically common situation. So about 20 days of maturation. As you increase the proportion of majors, then of course you get less minors, which makes a lot of sense, and more major workers. And you get 0 minor guards, which is good because we have no replacement, and increasing number of major guards. But if you start to decrease the maturation time, then you start getting this behavior where you could think, oh, there's a maximum there. That's cool. We should like get close to getting a larger number of guards, like peak the number of guards that are available for the colony. But that might actually be risky. A biological system will not operate that close to the existence conditions. It will be too close to extinction. So that could also mean that that could also be why there's selective pressure towards like longer maturation times. So the colony is able to sustain flexible amounts of major production. So with that, I'll just summarize the results of this. So first, all 3 timescales determine, all three processes determine the effect of the other processes. So it's not like you can just move one of those independently of the others and expect to have a positive result, like increasing the number of majors will not necessarily get you more allocation to guarding, and will not necessarily increase your colony size. So it will really depend on the others. And also accelerating maturation, that could seem like a reasonable way to respond to the demand for soldiers, may also reduce the survival range where the colony can exist. So those are just examples of pressures that might be acting on getting lower numbers of majors and longer maturation times. Now for future work, of course, there's many things to be done. One of them is to explore other shapes for the replacement function, because a step function is not realistic. It might be a good approximation. It have to be more detailed, more studied. But of course, a graded response could be considered, and in that case, we wouldn't have a Filipov system, but some other dynamics that switch between 2 main states. And also, it's worth analyzing that we just considered demographic factors, so colony size and task allocation, right? But there's other things like the risk that being unprotected represents for the colony. So if I don't have any guards, there's a higher probability that I'll get robbed or attacked, and that's its own risk, and that could be considered as in the model as well, and it's not being explicitly included. And also, of course, like the amount of food that these big bees require, that is larger to the minor bees. And then for larger applications, as I said, like this is not only applicable to stingless bees. There's many other insects that have these 3 processes. So H. polyethysum is very common. These morphological specialization is common in ants and in other bees too. And flexibility is also widely spread. And not only social insects, but also artificial systems. You may think of like little robots doing different things, and some of them are in charge of maintenance, and others are specialized for a certain task. And also in just the human defense domain, you may have just a team where people are dedicated to different tasks, and that's this is still, the general dynamics are applicable to all these things. So worth thinking about. And yeah, with that, these are the 2 main references that I would look at if I were interested in learning more. One is the more biological part of the stingless bees and these dynamics. The other one is about mathematical models of social insect dynamics, and that's from Dr. Kang here. And that is all I have. So thank you so much to the organizers and to all of you, and also to my others, Yoon and this other wonderful team